So to solve linear equations using matrix methods, first you need to understand how to express linear equations in matrix form. First, so let us take example 2x plus 3y is equal to 5, x minus y is equal to 2. So you have a set of linear equations. So how do you express this in terms of matrices? So we express this in terms of matrices like Ax is equal to B, where A is called the coefficient matrix, X is called the variable matrix, and B is called the constant matrix. So you express these equations in the form of Ax is equal to B. So A is the coefficient matrix. First you write all the coefficients. X coefficient is 2, Y coefficient is 3, X coefficient is 1, Y coefficient is minus 1. So the coefficient matrix is usually a square matrix. And next you have the variable matrix, which is a column matrix. So what are the variables in this equation? X and Y is equal to, we have the matrix B, which is also a column matrix, which is called the constant matrix. That is the constants 5 and 2. So this set of equations can be expressed in matrix form in this way. So if you expand this, you get exactly the same equations, because how do you multiply matrices? Row and column. So 2x plus 3y is equal to 5, x minus y is equal to 2. So this is how we express it in matrix terms. So let us take another example. X plus y minus z is equal to 3, 2x plus 3y plus z is equal to 2, x minus y plus z is equal to 1. So how do you express this in matrix form? So matrix, the coefficient matrix, write all the coefficients. 1, 1, minus 1, 2, 3, 1, 1, minus 1, 1, times the variable matrix. The variables in this column are x, y and z, is equal to the constant matrix, that is 3, 2, 1. So coefficient matrix into variable matrix is equal to constant matrix. So if it is a 3 by 3 matrix, you get a 3 by 3 coefficient matrix. And a column variable matrix is always a column matrix, constant matrix is also a column matrix. So as you can see, if you expand, if you multiply this matrices and equate it to this matrix, you get exactly these three equations. So every system of linear equations can be expressed as a matrix form, a matrix equation. Coefficient matrix into variable matrix is equal to constant matrix. So now once you express this, once you express the set of equations in this way, you can very easily solve it using matrix methods. For example, if you take the matrix equation Ax is equal to B, so what you need to find out is this variable matrix. You have to find the values of x and y. That is, you need to find the matrix X. So what I do is, I'll pre-multiply both sides with A inverse. So A inverse times Ax is equal to A inverse times B. A inverse into A is I times x is x. This implies the variable matrix is nothing but A inverse times B. So if Ax is equal to B, x is equal to A inverse times B. That means if you can find the inverse of this matrix and multiply it with the constant matrix, you get the answer, you get the solution of the equation x and y. The same is here. So here the crux of this concept is that Whenever you have an equation of the form Ax is equal to B, you just need to multiply it with A inverse on both the sides. And A inverse into B will give you a column matrix which is exactly equal to the variable matrix. That is the solution. That means a unique solution exists as long as A inverse exists. So in terms of matrices, as long as the coefficient matrix is non-singular, we have seen that inverse exists only for non-singular matrices. So as long as the coefficient matrix is non-singular, that is det A not equal to 0, you can always find A inverse into B is a specific matrix, you get unique solution. Unique solution. If that A is equal to 0, then you will have a problem. Let us see the cases depending on what det of A is. So now let us look at the criteria for consistency. Criteria for consistency. So before going into this, the set of the system of linear equations can be broadly classified into two different types. The system of linear equations can be broadly classified into two types. The first is non-homogeneous system, and next is homogeneous system. So what is a non-homogeneous system? So if you have the system of equations like Ax is equal to B, where B is a non-zero matrix. So if the constant matrix is a non-zero matrix, we call it a non-homogeneous system of equations. So Ax is equal to 0 is called a homogeneous system of equations. So whenever a question on system of equations is asked, quickly, the first thing that you need to check is whether the given equations are non-homogeneous equations or homogeneous equations. So if the left hand side or the constants are all zeros, we call it a homogeneous system. If at least one of them is non-zero, we call it a non-homogeneous system. So now in the non-homogeneous system, we have three different cases. So first, if det A is not equal to 0, so if det A is not equal to 0, then X is equal to A inverse times B. That means you have a unique solution. A unique solution. A inverse into B. If that A is not equal to 0, then A inverse exists. So X is equal to A inverse times B. Next. So the next case is if that A is equal to 0. So if that A is equal to 0, obviously we can't find A inverse, because A inverse is adjoint of A by det A. So if that A is equal to 0, A inverse does not exist. So I cannot multiply with A inverse. But what I do is, I'll multiply both sides with adjoint of A. So adjoint of A times Ax is equal to adjoint of A times B. So what is adjoint of A times A? It is det A times I, right? So det A times I into X is X is equal to adjoint of A times B. So det A is equal to 0. Det A is equal to 0. So this side becomes equal to 0. So now if adjoint of A times B is also equal to 0, then you have infinite number of solutions. If adjoint of A times B is not equal to 0, that means for whatever x, y, z, this side is always equal to 0. But if this side is not equal to 0, these two can never be equal. That means you have no solution. So what are the cases? If det A is equal to 0, the first case is if adjoint of A times B is equal to 0, then you have infinite solutions. And if adjoint of A times B is not equal to 0, then you have no solution. So these are the three cases that you have. Det A not equal to 0, unique solution. In the case det A is equal to 0, you have to find adjoint of A times B. If this is equal to 0, then infinite solutions. Not equal to 0, no solution. So you have three different possibilities in non-homogeneous equation. Now if you go to homogeneous equations, so there are only two cases. If det A is not equal to 0, so you can pre-multiply both sides with A inverse. So you get A inverse AX is equal to A inverse times 0 is 0. This implies X is equal to 0. That is a unique trivial solution. Trivial means all 0 solution. So if det A is not equal to 0, so all the variables, all the unknowns have to be equal to zeros. So if det A is not equal to 0, all the variables or unknowns have to be equal to zeros. If the second case, if det A is equal to 0, if det A is equal to 0, we again do the same thing. Instead of multiplying with A inverse, we multiply both sides with adjoint of A. So adjoint of A times AX is equal to adjoint of A times 0 is 0. This implies det A times X is equal to 0. So this time the right hand side is automatically equal to 0. So that is, the right hand side not equal to 0 case does not arise. That means there is no case of no solution. So if det A is not equal to 0, you have unique solution. If det A is equal to 0, you have infinite solutions. So you have only two cases for homogeneous equations. So I hope you understand the cases for non-homogeneous system and homogeneous system. So det A not equal to 0, unique solution. When det A equal to 0, adjoint of A into B equal to 0, infinite solutions. Not equal to 0, no solution. And for homogeneous equations, no solution case do not arise. If det A is not equal to 0, unique trivial solution. If det A is equal to 0, you have infinite solutions. That means a non-trivial solution exists. Non-trivial solution exists. So for a homogeneous equation, if a non-trivial solution has to exist, then det A has to be equal to 0.